Okay, so here's another example of drag in class 17. I think this is video 5. And so we have a baseball that's thrown by a pitcher at 95 miles per hour through standard air. The diameter of the baseball is 2.82 inches. We want to estimate the drag force on the baseball. So first off, let's take our 95 miles per hour and multiply it by 5,280 feet per mile and 3,600 seconds per hour, and we end up getting 139.3 feet per second. We can take the Reynolds number from this, and that's going to be the velocity. I'm using U and V interchangeably here, by the way, times the diameter divided by the kinematic viscosity. And if we look up our kinematic viscosity for air in US units, we end up getting 1.57 E minus 4 foot squared per second. So let's put that in here, and so that's put this in here, 139.3 feet per second, and we're going to have a 2.82 inch divided by 12, so that's going to be feet, and then divide it by our 1.57 E minus 4 feet squared per second. And we're convinced that's going to be a dimensionless number. We are using the right parameters. And you get 208,600. No units because it's dimensionless. What's good is to take the log of this, and we're going to find that's going to be 10 raised to the 5.32. And that's useful when we're doing a log-log scale, because what we can do now is go back into here and go to either this guy, or we could come up to him and take a look, and we can see, okay, so this is going to be like a smooth sphere, or we could assume it to be a smooth sphere, and 5.32 is like about 1/3 of the way between 10 to the 5 and 10 to the 6. So here you go, here it is right there. It's about 1/3 of the way, so I think we're still okay, and we're not into the dip-off region. So what I ended up using was about 0.4 for my drag coefficient. You could try to decide that it's going to be something a little bit more accurate than that. One thing I have done quite often is to see if I can find this quickly here. For many diagrams is to actually plot out or superimpose the diagram, a graph over the diagram. So let's see, did I do that on here? I did it over, did I ever, I think I did, I think I didn't like save any of these where I did it. So I'll copy this one over and show you that, because I don't want to mess up this one right here. So let's look right here, where you can superimpose and go on top of this by aligning the grid and getting everything, and then plotting out the points, right? So down below, what I've done is I've picked the points as carefully as possible, and now I know I have like a better idea of where that spot is going to be, right? So I could now, if I wanted to, plot in a point and see how close I laid it out to the blue. By the way, this other stuff is from a CFD analysis I just got done doing on a sphere. Decided to try to see if it matched, and I haven't reconciled while it's matched. I tried it in air and water, but I'm getting these same results. So it's something I'm a little frustrated on right now, but that's okay. But anyway, we're talking about like kind of like right there in that spot is where we're saying, and I think that is pretty close to the 500,000. No, excuse me. That should be the 200,000. So let me see if I could add a spot onto here. I go, what did I say, 208,000, 208,600. And let me plot that on there. My guesstimate is 0.4. Let's see how good of a job I did by adding that on there. So I'm going to add that spot and that spot onto here. And let's see where he is. Okay, there he is right there. Right, that's the spot I just added. I can format him if I want to and make him bigger so that you can see that that's actually the spot. So right there, boom, 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 boom. That is that spot right in there. So I guess 0.4 is not bad, but it's really got really close to starting to get into this dip where we're going to have a dramatically less. So I'm going to say that my drag coefficient is approximately 0.4. All of that effort for that 0.4, but it's right near there. So we're going to take our drag, it's going to be equal to CD 1/2 density times our velocity squared times the area. And so we have our 0.4 and 1/2. The density of the air, as we had mentioned or used before, was 2.3 E minus 3 slugs per cubic feet. So 2.38 E minus 3, and then 139.3 squared. And now for the area, that's going to be the cross-sectional area of a baseball, right? So pi over 4 times 2.82 divided by 12, and that's squared. So it's pi over 4 times the diameter squared. And we get a drag force of 0.4006 pounds. Now, my question is, does that make any sense, right? So we just got estimated the drag force, and what good does that do me, that drag force? Well, one thing I could do is I could look up a baseball weight, or the weight of a baseball. And what I got back was the weight of the baseball. I don't know why I have to write the subscript, but I did. Was about 5.25 ounces, OZs. Let's try to do a little bit of dynamics here and figure maybe just a couple things out. Let's see. Okay, now how much is the ball slowing down? Well, in order to do that, we need an FBD and an IBD, if you'll recall. And so I'm going to make the baseball traveling this way, that way. So it's got like I'll just kind of draw some stuff on it. So it's got a drag force that's happening in that direction. So therefore, it's going to have a acceleration, therefore deceleration, mass times the acceleration. And we can figure out how much that acceleration is going to be by taking the sum of the forces in the x direction equal to mass times acceleration in the x direction. We'll treat that direction as positive, even though both of these are going to be negative. And so we're going to say we have a negative 0.40006, excuse me. It's going to be equal to the mass of this, and that's going to be 5.25 divided by 16, because there's 16 ounces in a pound, divided by 32.2. And this is going to be, and by the way, this should be negative because this is pointing to the left as well. And we're going to get the acceleration in the x direction. Well, what we will find is that we will get 39.25 feet per second squared. Actually, it's going to be more than gravity. That's a larger amount than gravity. So that's a little surprising, and you start to question, does that make sense? Well, that's always does it make sense? Is a great engineering question. So let's try to find some other resource that would tell us, right? Now, according to baseballprospectus.com, let's see if I can find this website again. So I think I asked what is the drag force on a baseball? Or how much does the drag affect the baseball? And did I get that anywhere here? I don't remember the right search terms that I got, but it was like baseball prospectus, and it was deceleration. Maybe I spelled it wrong though. Maybe it was this guy, Baseball Prospectus, Eyewitness Scouting. I'm not going to find it really quickly right here, but it was talking about how much there you go, that there was the pitches and how much it would drop. And anyway, I felt as though it was a pretty good resource. And what it said to me was that from a pitcher's mound at 50 feet away, that a 95 mile per hour baseball, which was, by the way, at 139.3 feet per second, would lose as much as 10 miles per hour. So it'd be 85 miles per hour, which comes out to 124.7 feet per second. And so that's the acceleration. This is the pitch starting out there would decelerate to as much as this across the 50 feet. So if you wanted to find what the deceleration was going to be, you could take and find 2 times the acceleration times the change in position, and you could solve for acceleration, right? So we can go 139.3 squared is equal to, that's the final one. My bad. The final is so we went 124.7, and then we would have 139.3 squared plus 2. We're looking for the acceleration, and there's 50 feet. If we do that, what we find the acceleration is 38.54 feet per second squared. So that matches up really well to say that, yeah, I think this makes sense in terms of the drag force. So we've been able to throw some numbers at something and kind of decide whether this analysis or this amount of drag force actually makes practical sense. We can also see, by the way, that since it is close to being acceleration of gravity, that it would make sense that 95 miles per hour is probably pretty close to what the terminal velocity is of a baseball. That is to say, if you have a baseball that has a certain amount of weight coming down, right? And when you get the drag force equals the weight, you can work backwards and figure out what velocity would need to happen when these two equal each other. So this is no longer decelerating, it's falling at a constant velocity. And that's what we call the terminal velocity. When it's actually, even though it's still moving, it's in equilibrium. So that's kind of a cool problem to look through, and maybe that will be a homework assignment. So maybe if you made it all the way through this, you're going to have one leg up on everybody else.